Howdy everyone, I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I record all of my lectures. This is my Introduction to Data Analytics and Geostatistics course, and we are still in Lecture 2. This is the third video about probability. Now we start out with basic concepts of probability. What is probability? Frameworks for probability. Talked about frequentist probability, and now we're going to get into the good stuff. We'll talk about Bayesian probability. So let's go, and we were talking in the last lecture about a lot of Venn diagrams. We talked about the product rule. Let's derive Bayes' theorem directly from that. So first of all, the product rule is simply a readjustment or a shuffling of the definition of conditional probability. If we take the probability of B and we put it in the denominator on the left-hand side, that is the definition of conditional probability. And we could look at a Venn diagram and convince ourselves that that works. The probability of A given B, well, we shrink our universe down to only B, and we'll realize immediately that that conditional probability is the joint A and B divided by the probability of B. So we can see that this equation holds. Now, remember, B and A are just labels of events, and so we could reverse them. We could go both ways. It's not a big deal. So we can just switch B and A in different order, and we can go ahead and just calculate probability of B given A times probability of A, and so these both will hold. Simple. Now, we can go one step further, and we can tell ourselves that the probability of B and A is equal to the probability joint A and B. There's no logical reason that switching the order should change the joint probability, the intersection A and B. So we would expect it to hold that these are equal to each other. Now what we can do, we can take these formulations right here, substitute them into this somewhat axiomatic relationship here, and we get the combination of two product rules right here. The probability of A given B times probability B is equal to the probability of B given A times probability of A. This is known as Bayes' theorem. So this is super awesome. This got us to a very fundamental Bayesian equation that we're going to use to solve a lot of really cool problems. Okay, and I'll show you how we can integrate belief into it. Let's just step back and ask ourselves, why do we want to use Bayesian probabilities at all? Why use Bayesian approaches? Well, how are they different from frequentist approaches? We have probabilities based on degree of belief, which I like to say expert experience. Belief doesn't sound so scientific, but expert experience in an event. You're going to update it with new information as new information is available. And we're going to be able to solve problems that we could not solve with simple frequencies. Now, what's an example of a problem we can't solve with simple frequencies? Now, from the book Succe, their Bayesian tutorial, Data Analytics, is just an awesome book. And I recommend it. There's a second edition that's out recently. And in the first edition, I'm not sure, I didn't check the second edition, but they had an example of the question of the mass of Jupiter. I bet you they updated it. Because at the time of the book, 1996, when it was published or when it was being worked on, I don't believe there were exoplanets formally discovered. Now, please don't quote me on that. I'm not an astrophysicist, but from the book, I don't think they had that yet. And so the question became, what's the mass of Jupiter? And they said a frequentist approach would be measure the mass of enough Jupiter-like planets from multiple solar systems, and then you could from that formulate a distribution, make an estimate, figure out probabilities through an experiment and multiple measures. Now, the Bayesian approach would be you can form a prior probability and update with any available information. They said in this problem you could do that. We could use some knowledge about solar systems formation. We don't have an experiment to use, but we could use belief or expert knowledge about systems, and we could update with any other available expert information, new information, and we could get to a probability using a Bayesian approach. So let's go ahead and make a couple more comments on the Bayesian approach. The probabilities are going to be based on a state of knowledge, a degree of belief in an event. will utilize an assessment of prior to data collection knowledge. We'll start with a prior. We'll update with new information that's available. We'll solve probability problems that we could not solve using the frequentist approach. There's no space outside of the experiment for the frequentist. It's all about counting and ratios. They can't incorporate belief in that framework. Advanced concepts here. Well, the Bayesian approach, it's interesting. When we get into confidence intervals with the frequentist approach, we're going to realize that the Bayesian approach actually has what's known as credibility intervals. And they're actually a more intuitive measure of uncertainty in a statistic with regard to the population parameter. So, kind of cool, the Bayesians, there's a win for the Bayesians again. The belief and more intuitive credibility intervals. So, we'll get to that later. I just want to throw that in, get people interested. You can skip to that lecture, but Bayes' theorem. So, we just do a simple manipulation of the equation. We take the probability B, we put it in the denominator. This is the most common formulation of Bayes' theorem. And what you can see very quickly, we'll make some observations here. What you can see is that we can do a form of conditional probability inversion, which is really, really cool. And I'll show you with a couple examples that we can often calculate this conditional probability B given A. We can't directly calculate that, but we can go from here to this, and this is the one you really care about. And so it's very valuable to be able to do that inversion. The other way to look at it is this term right here is known as the prior probability. That's given your previous belief before you gathered new information. This is the likelihood. That's integrating new information of data you just collected. And this right here is the evidence term. It's a form of standardization. What's interesting is that the evidence term usually is just ensuring closure for the posterior. And the posterior right here is the updated probability. We went from prior, new information, and the posterior is the updated. Very, very powerful stuff. Now, I want to give you one warning here, and that is the prior should have no information from the likelihood or from the new data. This is known as peaking, statistically or probabilistically speaking. You can't use information from the new data to formulate your prior. Otherwise, you're double dipping, and you will prematurely shrink your uncertainties. It's not fair. You're fooling yourself into thinking you know more than you actually do. Likelihood and priors must not be sharing information. That's very hard to do. All right, so just to rename this and give you maybe a more intuitive expression, we could say the prior is the probability of the model. The likelihood is the probability of the new data given our model. The evidence term is the probability of the new data, which is actually really cool. And the posterior is the probability model given the new data. It's the model updated by the new data. So this is very powerful stuff right here. Now, it turns out that pesky evidence term is often very difficult to calculate. It really is. The best way to calculate it is a form of marginalization. And so what we could do is we could calculate the probability, in this case, probability of A, by calculating the probability of A and B plus the probability of A and B complement. And so we would expect that's equal to the probability of A. And by the product rule, we can substitute the probability of A given B times the probability of B plus probability of A given B complement times the probability of B complement. Now, so we went from this original formulation right here to this one right here. And you might think, oh, that looks like kind of a step back. It's more complicated. It turns out we have all these terms. In fact, look at this right here. This is half of it right here. So it's just the numerator again. And this part right here is the complement of B not occurring. And you'll find that we can often get access to that. I'll show you demonstrations where we do this calculation of the evidence term, and I'll show you how practical it is. I'll even introduce the concept of true positives and false positives and so forth. So it'll become very intuitive. Okay, so let's give you a class of problems over which we can use this formulation that will be very powerful. Let me just introduce it like this. It is the class of problems for which you have the probability it looks like it's happening, something is happening, given something is happening, but you really want to know the probability something is happening given it looks like it's happening. In other words, you want to know the probability something's occurring given a test has shown that it's occurring. Because you see, those are two different things. Having a positive test that looks like it's happening is not the same thing as it's happening. The test is not perfect. So let me give you a set of examples. Now, this first one, I'm not being at all flippant, but it is a good way to get it into your mind. And this would be the case of you go to a doctor's office, and event B is you test positive for a disease or some type of condition. What you really want to know is event A, whether or not you have the condition or the disease. You see that? Those are two different things. You might have a situation more subsurface speaking, or would be the geologist says there's a fault. That's the indicator, the test. But we really want to know if there is a fault. Laboratory measurement shows some low permeability. Well, there's an error in the measurement. And so we really want to know not the indicator, that it's the test being positive. We want to know whether or not the sample really is low permeability, and so forth. So we can go through all kinds of problems that are around this area of it looks like it's happening, but what I really want to know is something happening. Okay, given it looks like it's happening. Okay, so let's go ahead and just make a couple more comments about these classes of problems. If you look at that equation, this conditional probability, the likelihood, is the correct detection rate. The probability it looks like it's happened given something is happening. That's the correct detection rate. And we're multiplying it by an occurrence rate, the probability that it could be happening. Is it a very rare condition? Is it very common? That'll have a big impact on the result. And this denominator is the all detection rate. This is a true positive rate, and the complement was the false positive rate shown right here. Okay, so let's go ahead and pick an example problem and work it out. Now, this is a nice intuitive one. Prior information at a site, a subsurface environment, suggests channel feature exists at a given location with a probability of 60%. If there's a channel feature, that might have a major impact on subsurface flow, volumetrics. It's important to us. We decide to further investigate this information using seismic data. The seismic survey can show the channel feature is present with 90% probability if it's present. And if not present, with 70% probability if it really is not present. Okay, so let's go ahead and look at these probabilities, and let's put them into A's and B's so we can plug it into our equation and make it simpler for us. The probability, well, A event is the feature is present. The channel feature is present in the subsurface. B is the seismic shows the feature. A complement, the feature is not present in the subsurface. There's no channelization in the subsurface. And B complement, seismic does not show that there's channelization. Okay, so what do we have and what do we need to calculate? We have the probability of A. That right there is our prior probability. That without shooting seismic, there's a 60% chance from our degree of belief before we have the seismic information that we have channelization. Okay? 60%. So probability of A, 60%. 0.6. Probability B, given A, that's the probability of seismic indicates there's channelization, B, given there is channelization. And we said if it's present, channels are present, 90% probability that seismic's going to show it. Okay? So 90% probability of being able to detect it if it's there. But we said if it's not present, it's going to say the feature is not present with 70% if it's not there. So the probability of seismic saying it's not there, B complement, given it is not there, is 70%. So a little bit more difficult, more challenged to be able to determine that. It's not quite as high as 90%. Now, the rest is just going to be plug and chug. Here's the equation right here. We're missing A complement and we're missing B given A complement. How do we solve for those? Well, remember closure. The closure relationships that we had with the complements. Okay. Now, that's enough hints for now. I'll go ahead and show you the solution in 3, 2, 1. Here you go. Okay. So once again, just by closure, probability of A complement is 1 minus probability of A. That's going to be 40% chance before you shoot seismic of just not having channelization. Probability B given A complement is going to be just simply equal to probability 1 minus the probability of B complement given A complement. So we shrink our universe to A complement, and now we can say that the probability B complement plus the given A complement and probability B given A complement, they sum to 1, so we get 30%. We can plug and chug, and immediately we should recognize the numerator is the true positive detection rate, true positive, false positive detection rate. This is all detections. The evidence term is the probability of all detections. Okay, so there we go. And we get 82%. Do you shoot the seismic? What do you think? If the seismic shows channelization is present, there's 82% chance there is channelization. The prior was 60% chance. That's a pretty big improvement in certainty. Seismic could be valuable. Now, the cool thing, if you were working in decision analysis, those probabilities are exactly what you would need to figure out the value of information and solve for this problem. So, another win for Bayesian statistics right there, Bayesian probability. Okay, here's another example right here. We'll work this one out too. 1 in every 1,000 blowout preventers, BOPs, has serious crack. They just have that problem. X-ray analysis has a 99% chance of detecting a crack correctly. In other words, saying there's a crack if there's a crack. If the BOP does not have a crack, there's a 2% chance of the X-ray detecting the crack. That's a false positive of 2%. Okay, false positive rate. And the rate of blowout preventer cracks is 0.1%. So that is the overall prior of having those cracks occurring. Okay, the blowout preventer has been X-rayed and the result is positive. What is the chance the blowout preventer actually does have a crack? Okay, so let's define events. A, blowout preventer has cracks. Okay, the thing is happening. B, the test indicates it has a crack, the X-ray test, and the A complement and C complement. What do we have so far? We have the probability of A. The prior, we said it's going to be 0.1%, 0.001 is the crack rate just overall. We said the true positive for the X-ray test detecting a crack, given there is a crack, is 99%. And we said a false positive rate of detecting a crack, given there is no crack, is 2%. All right, so let's go ahead and work this out. I will show you the solution in 3, 2, 1. And here it is. Okay, we were just missing the A complement. We had everything else we needed. Not a big deal. Using closure, simple closure, we can say that the probability of A complement, there's no crack in the blowout preventer, is 0.999. Okay, so then we just go ahead and we can plug and chug. And what do we find out? We find that the probability of a crack in the BOP, given a test is positive for a crack, is only 4.7%. Whoa. So what happened? What kind of wrecked our test here? And what happened here, the cracks are very unlikely. The rate of cracks is so small, 1 in 1,000, right? And so because of that, and the fact that we have kind of a large false positive rate, the false positives swamp the equation. We end up with a high number here, low number here, low number here, and we get overall a low percentage for the conditional of having the crack given the test was positive. Okay, so this is it. Now, what's really interesting, and I did show this lecture previously, and I got really good feedback on my YouTube channel. And they said, well, no, I object. I think it's a good test. And let's talk about that. The prior probability of crack was 1 in 1,000. After you run the test, you're now up to almost 5%. Now imagine that. You've gone from thinking there's 1 in 1,000 chance, 0.1%, and now you've gone to almost 5% probability of having a crack. This is not a conclusive test, but this is a very, very good indicator. If you can do this cheaply and quickly, it would actually make sense to run this on the blowout preventers because you're greatly changing that degree of certainty. Okay, so we're greatly updating. It could be seen as being valuable still. All right, I hope that was to you. If you want a little more hands-on experience, I've worked out an Excel spreadsheet where I take this basic Bayesian formulation and I run the experiment in which you get to change the yellow cells. You get to change the prior probability of the thing happening, the positive and false detection rates and so forth, and then observe the overall conditional probability of the thing happening given the test was positive. And it provides all kinds of outputs and explanations and so forth. You can play with the numbers. Not a bad idea. Everybody can work with Excel. And here's some ideas of things to try. If you want to get a hold of this spreadsheet that's well documented, it's available to you on my GitHub repository in my Excel numerical demos specific repository under Geostats guy on GitHub. I just want to make some general comments about what we just learned. A combination of rare events and high false to positive rates can make conditional probability of an event given an indication very low. We calculate the posterior and we can compare it to the prior and use this to assess the value of the information of the test. So that can be very useful to us. We go from the prior probability something's happening before the test to probability something's happening given it looks like it's happening from the test. And that's a good way to measure the usefulness of our test. Now I went to Wikipedia and they had a really nice example of a Bayesian problem. And I thought this was a really good one to share because it's a different class of problems, but it does demonstrate how we can use Bayes' theorem to solve things actually that would be kind of tricky without using a Bayesian approach. Okay, so we got three machines, machine 1, 2, and 3, and they produce products. 20% of the production comes from 1, 30% from 2, 50% from machine 3. They're mutually exclusive. Okay, X1, X2, X3, machine 1 through 3, mutually exclusive. Each sample only comes from one, but it's exhaustive. Every sample has to come from one of them. The error rate on each one of the machines are different. Apparently we got some better machines, worse machines, maybe the crews work in them, maybe night crew or something, but there's a reason, there's a difference. The machine 1 has a 5% error rate on the products. Probability of error, y is equal to error, given x1 is 5%. Probability of error given x2, machine 2, 3%, and 1% for machine 3. What is the probability of an error in the product overall? Now what's cool, what would be a hint? How do you solve this? What we want to do is marginalization. We want to sum across all of the machines. Because they're exhaustive and mutually exclusive, we can use this formulation right here. Probability of y is just going to be the summation of the probability of y and machine x1 or x2 or x3, or the summation of the probability of y given the machine xi times the probability of xi. And you do the sum over the three machines, we can go ahead and get that. Let's go ahead and solve that. All right, so give it a try. I'll show you the answer in 3, 2, 1. All right, so this was pretty straightforward. All we had to do is plug and chug. We have mutually exclusive exhaustive events, so we're able to just do the summation of the joints y and xi's over the three machines. We can expand it using the product rule, and we get this formulation right here. And so we find out that the probability overall error rate is going to be 2.4%. Now, if you think about it, it's effectively like a weighting based on the percentage or proportion of production coming from each one of those. That's another way to think about this. A weighting of the error rates by the amount of production coming from each one of the machines. Now, that was super easy, but we needed it. It's now the evidence term because that's the probability of y overall, and we can use it now to use Bayes' theorem and solve harder problems that are less intuitive. What's the probability a product came from each machine given an error was observed? Now this is the probability inversion, the conditional probability inversion that I talked about before. What's the probability of xi from machine 1 or 2 or 3 given there was an error y? Okay, so we already got the evidence term, probability of y is 2.4%. All we have to do is calculate the conditional probability from Bayes' relation. We want the probability of coming from machine I given an error, and we could solve it like this. And what you can see immediately, this would have been hard to do directly. But this is much more intuitive and easy to work out, and this was easy to work out too. I'm going to show you the answer for each one of the three machines in 3, 2, 1. Look at that. Isn't that awesome? I just love it. So this is the formulation. No surprises. We already showed that to you. We can plug and chug. We get the probability of an error given machine 1 of 5%, probability of coming from machine 1 is 20%, 20% of the production, divided by the evidence term of 2.4%, and we get 41% or 0.41. That's the probability. If there's an error in the product, there's a 0.41 probability that it came from machine 1 and machine 3 and machine 2. Now, they're mutually exclusive, exhaustive, so we would expect if we do the summation over all of these three, that it will sum to 1. And that makes sense, right? The probability of machine 1 given an error plus probability of machine 2 given an error, probability of machine 3 given an error. Well, that should have closure in the conditional sense. Now I provide a really nice example of using Bayesian probability in the case of exploration. And so this is a spreadsheet that's well documented. It's available to you on GitHub at this link. It's within my repository, Excel numerical demos, under my account Geostats guy. Now, what are we doing here? So you have some type of prior probability for the exploration success rate. So what's the probability of exploration success of 35%? 10%. 45%, 20%, and so forth. Now, if you take all of these, I just entered them, we can standardize them so they sum to 1. So now 45% becomes 50% probability, 25% probability, 25% probability for the 45% as the mode, and 35% and 55% shown right here. If you visualize that distribution, that orange distribution is the prior distribution. It's our distribution for success rate prior to new information. Then what we do is we enter in new drilling outcomes, the new information that we have available. So we had 30 wells drilled, 10 success, 20 failures. We have in the recent drilling campaign a success rate of 33%. Now you notice our prior was saying about 45% was our mode, our most likely success rate in our exploration program, our wildcat drilling. Now what we can do is we can use Bayesian probability to get the posterior, to update the prior with the new drilling information, likelihood to get to a posterior. Now, how do we calculate the likelihood distribution? Not a problem, really simple to do, because we in fact have the outcomes of the recent drilling. We had 10 successes, 20 failures out of 30 in total. So I can go down here and say, what is the probability of that outcome given a success rate in our exploration actually is 0.05? That right there is going to be the probability of the result given the model, the success rate of 0.05. And we can solve that for all of these possible success rates in exploration. And that will give us the blue distribution right here. Now, if you look at it, it actually makes real sense because you see where the mode is? The mode is actually at about 33% or 1/3. So it makes sense that's the most likely outcome given what we observe with the data, and it diminishes both ways. It becomes very unlikely that the success rate in exploration, given these observations, is something like 80%, 90%. It's so far away from what we observed in the success rate. So we got a prior distribution from belief or previous experience. We got a likelihood distribution from new results, right from the binomial distribution. And we'll talk more about parametric distributions later. And we got the green distribution is the updated distribution, the posterior distribution. And so this spreadsheet allows you to actually play around with and use Bayesian updating, Bayes updating, in order to solve a really interesting problem in exploration and drilling. Now, if you want to work with entire distributions with Bayesian probabilities, it turns out that in the case of a Gaussian distribution, if we assume the prior, likelihood, and posterior are all Gaussian, and in a couple lectures we'll define and work with Gaussian distributions, but it's that nice bell-shaped curve distribution. It turns out that we can calculate the updated or posterior mean and variance directly from the means and variances of the priors and the likelihoods. So it's really simple. There's a closed form analytical solution. It was shown in the Succe book on Bayesian updating. Now let's make an interesting observation. If we go down here and look at the variance of the posterior, you're going to immediately recognize the fact that none of the means from the likelihood of the priors are in the equation. In other words, the degree of variability in the posterior is not dependent on the central tendency or the location of the Gaussian distributions for the prior or the likelihood. This is known as homoscedasticity. The amount of variation is consistent over the values of centrality. All right, we'll get more into that later on. It just cheers me up to use the word homoscedasticity or heteroscedasticity. We'll talk more about it and formalize all of this. But we can do Bayesian updating with Gaussian distributions. Here's another spreadsheet, Bayesian Gaussian demo on my Excel numerical demos. You can play around with the yellow cells here, change the average and variances of the prior and likelihood distributions, and it'll calculate the posterior mean and variance. And so you can go from prior, the yellow line, the CDF right here, Gaussian, the S curve, nice shape there. You can take the likelihood, which is blue, you just put that in, and you get the green, which is the posterior, the updated with Bayesian updating. Very powerful stuff. Now, of course, we have cases in which we're working Bayesian probability, and we're working with multiple mutually exclusive events. And our machines were doing that, in fact, right? The product had to come from one of the three machines. There was no other choice. In that case, we can just make the comment, as we did with the machines, that we can calculate the evidence term in a pretty simple manner. We can go ahead and just do the summation of all of the joints. Now, be careful if you don't have mutually exclusive exhaustive events. You can't do this. But so we can just substitute the probability B is just being the summation of the probability B and the multiple A events, A1 through K. Okay, so I hope this was helpful to you. This has been a lecture on Bayesian probability. So we've covered what is probability in the first lecture, just some general comments about frameworks or how we could think of probability. The second lecture, we talked about the area of frequentist-based probability. And in this last lecture, this one just now, we derived Bayes' theorem and then used it to solve a lot of problems that would have been very difficult to solve using just frequentist approaches. All right, I hope this was helpful to you. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. I record all my lectures, put them online to support my students. Shout out to you guys. Keep working. We're getting through the term. And also to support working professionals or to remove barriers. I love the idea of folks, maybe high school students or someone who's not currently in university, thinking about opportunities to go into science and engineering. We need more STEM. All right, everybody. I hope this was helpful. Take care.